So this video is on the Taylor series, and you'll have three main learning objectives for this part of the class. First of all, you'll know what a Taylor series is based on its mathematical definition. Second, you'll understand why that mathematical operation works. And then third, you'll know how to compute a Taylor series of any function. So what is a Taylor series? So a Taylor series is a sum. That's what makes it a series of functions that is used to approximate another function and we'll refer to that function of f with an independent variable x, and in the vicinity of x near a specific value of xa. So you might ask why we would approximate a function with a sum of other functions. Well, oftentimes the function we're trying to approximate is relatively complicated, or makes its form is hard to use in solving a particular problem. And you'll see that Taylor series is a very powerful way to use relatively simple functions to approximate that function, again, only where x is near a specific value of a. So our example is an exponential decay function. And so we will set f of x equal to a constant 10 times e to the minus 2x. And that's shown by this gray curve. So let's approximate that function near, let's say that we're going to approximate that function as it varies about x equals a. So f of x is approximately, the first approximation we can make is just to set the value of f at location a. And here we're going to set a equal to 0. So let's approximate f at x as equal to f at 0. So if we put x equal to 0 in here, we're going to get a constant function. We're going to get a constant of 10. So if we were to plot that function f equals 10, we see that it exactly matches the function at x equals 0. But as we move away from 0, this function deviates from the real function. So this function is only a good approximation to the whole function right at x is equal to 0. And we're going to refer to this as the 0th order approximation to this function. So let's consider a first order approximation. How can we do slightly better than just this constant function? Well, for one thing we could do is consider the slope of this function at x equals 0. So we can say that f of x is equal to f at 0 plus the slope of the function, which we will denote as f prime, the first derivative of f with respect to x. The slope of that function at x equals 0 times x minus 0. So if we take the slope and we multiply it by x, the deviation of x from 0, then we will get a function that slopes downward. So evaluating these different terms, we get f of 0. So e to the minus 2 times 0 is just 1. So we get a 10. And then the first derivative of of the function at evaluated at x equals 0 is 10 times minus 2 times e to the 0, which is equal to 1. And then we have to multiply that by x minus 0. So this gives the function 10 times 1 minus 2 times x. So we get the function starting at x equals 0 of 10, and then we get a line that slopes down at minus 2 and, as a function of x. And you can see that downward sloping line follows the gray curve. I mean, it hits, as expected, it'll be tangent to the gray curve at x equals 0, but it follows the gray curve pretty well for, a reasonable range of x in this case. And that's our first order approximation. So let's look at a second order approximation. And for that, we're going to approximate f of x based on its value at our starting point plus the mean slope between 0 and our arbitrary value of x. And that has to be multiplied by our distance from x. Our distance from 0. So this is our mean slope. And so rather than using the slope only at x equals 0, we're going to take the slope average between x equals 0 and x equals x. So our mean slope is approximately the slope, that is the first derivative, f prime, at x equals 0, plus the slope, the slope or f prime evaluated at x. And if we divide that by 2, we'll get the mean slope. So what is the slope evaluated at an arbitrary location, x? Well, that's equal to the slope evaluated at x equals 0, plus the rate change in the slope of the slope evaluated at that location times the distance. So just as we took the function itself, took the starting point, and sketched a line along the function itself, we can take the slope of the function evaluated at 0 and show how that slope varies linearly away from that location. And so therefore we get the mean slope, m bar, is equal to f prime 0 plus f prime, this term, 0, plus f prime prime evaluated at 0 times the distance from x divided by 2, and that's equal to f prime 0, so we have 2 of them divided by 2, plus f prime prime times x minus 0 divided by 2. And so when we put this back in our function, we get f of x is equal to f0, our starting point, plus our mean slope, which is f0, f prime evaluated at 0, plus f prime prime times x minus 0 divided by 2. And then we have to this is our mean slope, and we have to multiply that by our distance. Okay, so again, we multiply this by our distance, and so we have an x minus 0 there, and we have 2x minus 0s on this term. This is our second order approximation. So when we fill in the values here, f of 0 is still 10 times 1 for the 0th order term, minus 2 times x for this first order term. And then we have plus the second derivative of 10 times e to the minus 2x. So the first derivative was 10 times minus 2 times e to the 0 power. That was the first derivative. The second derivative, we have to multiply this again by minus 2. So that'll be 10 times minus 2 times minus 2 times e to the 0 power. And so we get positive 4 e to the 0 power, which equals 1. And then we get x squared, because we have to multiply that by that. And this gives, and then we get a 2 here. And this is our third order approximation. So you can see that by using this mean slope, we get a second derivative and a curvature, because we have an x squared term here. We get curvature to our approximation, and that curved approximation follows the gray curve even better further out away from x equals 0. So that was the approximation with 3 terms. This is the approximation with a 4th term, which is the third order approximation. And you can see that these red dots follow the gray curve even further out. So let's write out the general Taylor series expansion. And so we will say that f of x is equal to the Taylor series expansion of f at about point A, the expansion about point A, and that's equal to f evaluated at A plus the first derivative evaluated at x equals A. Remember, in our example, A was equal to 0, but here this is the general expression, and we have 1 factorial. 1 factorial is just 1. And then we have to multiply that by x minus A. And then we add the second derivative times x minus A squared divided by 2 factorial. And then the third term, which I didn't show you, but I'm showing you now, is the third derivative, the third order term. It's the 4th term in the whole expansion, is the third derivative times x minus A cubed all over 3 factorial. And this continues actually on to infinity. We add an infinite number of terms. And when we had our special function, f of x is equal to 10 e to the minus 2x, we expanded it again about 0, but we can expand it about an arbitrary number, a, and that's equal to 10 times the function 2a. So 10 times e to the minus 2a was our function evaluated at point A, e to the minus 2a, and then plus the derivative of e to the minus 2x is minus 2 times e to the minus 2x, and we have to evaluate it at point A. The second derivative is this times 2 again, times x minus a squared, and this is all over 2 factorial. This is over 1 factorial. And then the third term would be minus 2 cubed e to the minus 2a times x minus a cubed over 3 factorial. And then we would add terms all the way up to infinity. So the more terms we add, the better we're going to approximate this curve. And if we add an infinite number of terms, then we will match the curve exactly. And just to maybe if we could write this out as, we could simplify this a bit, because everything's proportional to e to the minus 2a. This term gives us a 1. This gives us a 2 times x minus a. And then we get, this term gives us a positive 2 x minus a squared over 2 factorial. And 2 factorial over 2 factorial is just 1, so we can just not show that. So this is 2, I'm sorry, this should have been a 4 over 2 factorial. And so this gives us a 2. And then we have a minus 2 to the third power is minus 8. And 3 factorial is 1 times 2 times 3 is 6. And this is this gives us an x minus a cubed, and so forth. So that's this with this special function. I would like to show the Taylor series. We can write this in a slightly more compact form, and that looks like this. The function is equal to the Taylor series expansion of f about point A, and that is equal to the sum. So this sigma is, this is a sigma, or the Greek letter for S for sum. And in this sum, we're going to change j. We're going to start with j is equal to 0, and we're going to add 1, 2, 3, all the way up to infinity. And when we change j, we change the terms in the sum. So we're going to take f, and we're going to take the jth derivative, of f, and we're going to evaluate that at point A, and we divide by j factorial, and we multiply times x minus a to the jth power. So this term has j equals 0, 0 factorial is 1, and we have the 0th derivative. Here j is equal to 1, so we have 1 factorial, we have the first derivative, and we have x minus a to the first power, and so forth. And I'm going to write this, well, in practice, we could never add an infinite number of terms, even if we have a super huge computer, but we can get a good approximation, depending on our application, if we add n terms up to the n minus 1th derivative. So this would be f raised to the jth power, the jth derivative of f, evaluated at a, j factorial, x minus a to the jth power. And then to get the rest of the sum, we would add j is equal to 1 to infinity, and so forth. So by doing this is in practice what we do, but this here is our error, and it's denoted as r sub n. That's or r for the remainder, and r sub n is proportional. It turns out that r sub n is proportional to the nth derivative of f, and this is described as an nth order error. So as you saw, the higher order we took out in our expansion, the better the curve, the series matched the true curve, and the lower, therefore, the error is. So as we increase little n, we match the curve better, and the remainder, or the error from the true curve, decreases. So hopefully by now, you now know what the Taylor series is, you know why it works through the example we looked at, and you'll get some practice on computing Taylor series of different functions.